Hello, I'm Bernard Ziegler from the University of Arizona, currently Chief Scientist of RT-Sync Corporation. And I'd like to talk to you today about modeling and simulation in modeling of healthcare. In particular, I'd like to talk about a new exciting approach to reform of healthcare by Michael Porter called Integrated Practice Unit. And approach it with system of systems modeling and simulation. And this is prepared for the 10th National and International Conference of the Hellenic Society for Systemic Studies in Athens in May. Short overview, talk about healthcare reform as a systems problem, and look at Porter's work on fixing the healthcare system with the concept of integrated practice unit. We'll look at that approach from the point of view of systems theory and particularly the concept of system of systems, and use the Discrete Event Systems Specification, or DEVS, modeling and simulation framework to help us understand how to formulate this healthcare system as a system of systems. And we'll look after that at the role of our particular simulation environment from the MS4 Systems company and its implementation support for the concept of the integrated practice unit in healthcare delivery. Let's talk about healthcare reform as a systems problem. The U.S. healthcare system is the most expensive in the world. It can be considered as an assemblage of uncoordinated subsystems such as doctors, hospitals, labs, etc., embedded in a market economy, which promotes fee-for-services without reference to the end-to-end quality of care and cost delivered to patients. The major aspects of care in need of coordination to coordinate such systems are clinical and extraclinical. Clinical care refers to medical observation and treatment of patients in the usual way we consider care is offered, preferred by physicians, hospitals, labs, etc. And coordination is required in such care because the various specialists involved, and often in the case of more complex diseases which require many specialties, these treatments are often too loosely coupled. The doctors are not well coordinated, they don't share information easily, they don't share timetables, and are difficult to bring together on dealing with the same topic, same problem. And so they don't provide the best care at the lowest cost. Extraclinical care requires coordination of services to help patients deal with multiple tasks and decisions before and after they receive treatment in the hospital. In the hospital, almost all decisions are made by doctors and nurses, but once the patient leaves the hospital, they are more or less on their own. Let's discuss fixing the healthcare system. Michael Porter, who has been working on this problem for quite some time, advocates radical reform in which physicians should reorganize themselves into team-based integrated practice units. These units should be dedicated to a particular medical condition, for example, asthma, breast cancer, congestive heart failure, and so on. and provide a full cycle of care centered around such conditions. Porter defines patient value as the outcome of such a full cycle per unit cost after all treatment in the end-to-end care delivery value chain. This concept of integrated practice unit must be considered as an entire system. These components from which it's put together, doctors, hospital, labs, are currently fragmented into independent systems that include actors such as doctors and services, and so on. Our objective is to formalize Porter's integrated practice unit with system of systems modeling and simulation. We'd like to formulate criteria for creation of such IPUs viewed as systems. There are many questions that this kind of formulation can address. For example, can a collection of systems, each with their care delivery value chains, be integrated into a viable integrated practice that has a single care delivery chain that encompasses all of the relevant parts of the care delivery value chains of the components? Before proceeding, let's do a brief review of some relevant system theory concepts. The approach we're talking about is based on Wymore's mathematical system framework, which he discusses a composition of systems. This takes a collection of constituent systems and couples them together with a coupling specification. Coupling generally refers to the outputs of systems connected back into inputs of other systems. And this collection of systems together with the coupling specification results in also a system. And this system has a behavior emerging from the interaction of the constituent systems through these output to input couplings. If there's a closure under coupling, then the resultant system is actually a well-defined system, just like the original components. The Discrete Event Systems Specification formalism is a concept that's based on Wymore's underlying systems theory concept, and it defines two kinds of models, atomic and coupled. The atomic models are defined directly, and the coupled models are constructed by composition based on Wymore's concept. The component models in this case are Dev's atomic models and coupled models from earlier compositions, and coupling specification, just as Wymore's had. And this results in a Dev's with structure and behavior that emerge from the interaction of the components through the coupling. If there's closure under coupling, which is shown to be true under wide conditions, then the resultant, the system that results from this coupling of the components, is also a well-defined Dev's. Not just a system, but a Dev's. It has the same properties as a discrete event system specification is performed in creating atomic models, for example. And this supports hierarchical composition, in which the resultant Dev's can be used as a component with other components to create yet bigger, higher level systems. This is discussed in the book Theory of Modeling and Simulation. The MS4 company's product called MS4 Modeling Environment is a Dev's integrated development environment. Since Devs provides a computational basis for modeling and simulation using Wymore's system framework, it can support multi-formalism systems, in other words, systems that contain both discrete event and continuous models, and other models expressed in different formalisms, all in the same simulation environment. Here's a link to the MS4 systems description for this integrated environment. And noteworthy is that this integrated development environment for devs and for Wymore systems concepts supports working directly with systems thinking and systems engineering concepts. Let's look a little closer at the devs IDE support of systems. We can define component systems and the coupling specification in this environment and create for simulation a resulting system of systems. A system of systems is a composition of systems, which means it's got component systems, but in this case the components have legacy properties. That is, they don't come just made. They have been around in reality for different lengths of time, and they have properties that have evolved or have been developed for their current tasks and current contexts, and these must be all brought together to create a new system called a composition or system of systems. In addition, the coupling also has certain properties that we have to take into account that allow connectivity between the components and coordination and so on, sharing of information, sharing of exchange of energy, and so on. The structural and behavioral properties that result in such a system of systems can be characterized as in different ways, such as fragmented, for example, the way the current healthcare system is, competitive, which also characterizes the current system, collaborative, which is less characteristic of the current system, and coordinated, which is the kind of situation that we would like to bring about. With this system theory approach as background, let's look at a healthcare system model. Patient enters with a medical problem. The patient interacts with the healthcare system, the doctors, hospitals, labs, and so on. And finally emerges hopefully with an improved condition. The healthcare system itself, as we've said, can be decomposed into two parts, the clinical domain and the extraclinical domain. The healthcare system as currently constituted is uncoordinated and leads to high cost and less than optimal outcomes. Therefore, it requires coordination and even integration of its components to achieve better care at lower cost. Let's look at an integrated care system model based on Porter's integrated practice unit, but it applies both to clinical domain and to extraclinical domain. In the clinical domain, we have Porter's Integrated Practice Unit. Its components are physicians, hospitals, labs, and they provide services such as diagnostic services, treatment services, also recovery services, and follow-up services to provide an integrated practice unit solution, which is a full life cycle of care for a particular medical condition. The extraclinical domain, which we're adding in, also is needed to handle the issue of the patient's treatment before and after the clinical experience. So before going to the hospital, after coming out of the hospital, try and assure that the patient takes care of themselves and does not need to return to the hospital, which is a major source of extra cost. All this together constitutes the integrated care system that we're discussing. And notice that we are using hierarchical composition to put these major components together. First of all, the systems of systems, the physicians, hospitals, labs, and so on, into new proposed components such as the IPU and the Pathways Community Hub extraclinical coordination, and then these components into a bigger system, the integrated care system, and these are to handle both the clinical and extraclinical domains. Let's focus now on the integrated practice unit and on the care delivery chain for such a concept. This can be considered the architectural blueprint of the IPU. It lays out the organization of its components and their couplings, viewed as systems of systems. Following Porter, let's look at requirements for a properly constituted care delivery value chain. It refers to components such as the team members, and they must have the appropriate skills and services to populate the CDVC. The set and sequence of services must be aligned with the value. Remember, value is the outcome from the patient's point of view divided by the cost. And so the services, the choice of services and the sequence in which they are performed along the value chain must be aligned with this final outcome, which is what the patient is seeking in treatment. These services should have the right scopes to cover the target medical cluster of conditions and to minimally overlap. And then they must be coordinated into a coherent whole with seamless handoffs from one to the other, minimizing process delays and what's called dropping the baton in current parlance of treatment, where somehow inadvertently a patient is not transferred properly from one specialist to the other. Further, these services must be performed in the right locations with the right facilities. All this to enable a coordinated and efficient delivery of the value to the patient or the customer. And then the right information must be collected, utilized, and integrated across the care cycle. Let's look at characteristics of components and couplings in system of systems. These will be relevant when we consider how they are applied to the integrated care system, which we'll discuss next. Autonomy has to do with the system's ability to decide and act independently. It ranges from conformance to independence. Autonomy is ceded by parts in order to grant autonomy to the system, and therefore is a very important feature of the integrated care system. Belonging concerns the component's functional ability to qualify for participation in the system of systems. It ranges from centralized to decentralized. Connectivity, the component's capability to exchange information with other components, ranges from platform-centric to network-centric. Diversity, degree of notable differences among components. And this can be reduced or minimized by encapsulation and modular hierarchy, such as the hierarchical composition that we've discussed. It ranges from homogeneous to heterogeneous. Emergence is the appearance of new properties in the system not present in the components. Foreseen, both good and bad behavior, and designed in or tested as appropriate. It ranges from foreseen to indeterminate. When we look at the characteristics of systems in application to the integrated care system, we find some interesting associations. For example, autonomy, its application to the integrated practice unit, is assuming that the current situation, physicians are independent practitioners. How much autonomy must they give up to form the IPU team? Can they retain their economic sustainability if the IPU fails after ceding such autonomy to join the team? Belonging. Do physicians join the IPU on a cost-benefit basis? Do their skill sets match those needed by the CDVC? Can they adapt to provide needed services rather than the sophisticated ones they've brought to the table? Connectivity. Will the health information technology infrastructure support the increased communication needed to enable the increased coordination and integration that's required for this integrated care system? Diversity. Are the electronic health record systems employed by the providers either same or interoperable with each other? And do they interoperate at the three required levels, syntactic, semantic, and pragmatic? Do they provide the ability to synchronize to achieve common goals among the constituent systems? Emergence. How strongly can the emerging CDVC be predicted from the formal composition of the individual CDVCs? Now let's bring our modeling and simulation capabilities together with the system of systems concepts that we've discussed just before. Let's consider developing a modeling and simulation approach to testing various architectures for integrated care systems. We are given medical conditions such as asthma that we wanted to develop a IPU or integrated care system for, and certain patient populations, for example, youths in this case. And we have various alternative architectures to explore. How to formulate the care delivery value chain, various variations, the actors, doctors, lab technicians, services provided, such as we've discussed, and how these services are assigned to the CDVC, in which order, in which sequence, which set. And also we have to discuss designing the outcome measurement component, for which Porter provides a good guidance, but we will not further consider here. And then we can simulate the composition of these models to evaluate the patient value, which is the outcome as measured by the measurement component and the cost as measured by that component. Then we are in position to select the best architecture, or one of many possible bests, which are the model or the models which maximize outcome per unit cost. Now these variations in the CDVC and the actors and the services selected, how they are assigned to the CDVC, all are constrained by the system of system characteristics, which we'll discuss next. So, having selected certain conditions for autonomy, belonging, connectivity, diversity, we can create a integrated care system model, which is one of the architectures, and simulate it using the MS4 environment. And this will result in an evaluation of patient value, which is the outcome quality divided by the cost as measured by the measuring system. And then we can compare that with earlier explorations of the architectures and try a new architecture with different characteristics, slightly different, or make major changes, and then repeat this cycle until we come upon good or best architectures. Let's draw some conclusions from our discussion. We've made the case that healthcare reform can be usefully viewed as a systems problem, and that Porter's integrated practice unit, considered within a more inclusive framework, the integrated care system, provides the needed coordination and integration to provide the basis for such reform. We formalize the integrated care system using the system of systems theory as expressed in the DEVS modeling and simulation framework. The MS4 modeling and simulation environment, which is based on the DEVS framework, supports design, implementation, and virtual test of such integrated care systems, and allows this kind of healthcare reform to be done in a more engineering manner, in fact, using the systems engineering approach. I hope I've whetted your appetite to look into more details and more of the problems that can be addressed using the framework discussed, and perhaps try an experiment with it yourself. Thank you.